Hello again. This is a video on chapter 5, trigonometry. So we're going to continue with what we did last time and talk more about angles and the 6 ratios. So let us get us started right away. I hope you're doing so we are going to talk about unit circle, which is the foundation of modern trigonometry, and the ratios. For now, let's talk about the idea of unit circle and how useful it is. Now remember that an angle right here, if the radius is 1, then the arc length from here to here is given by r times theta. But if the radius is 1, then the arc length is the same as the theta in radian, right? This becomes really useful because now we can think of a number line. So this is the positive numbers, number line 1, 2, 3, 4, and so forth. And then this part is the negative number line, negative part of the number line with negative numbers. We can think of the angle, the arc length, as a real number. How? We take this number line and wrap it around the circle this way, the positive part of it, right? And we assume the thickness doesn't have thickness, so we can wrap it around forever. It means every angle can correspond to a real number on this positive, number line. So for example, let me clean this mess a little bit. So for example, if we are thinking of 1 radian, which is about, 57 degrees. So if this is 1 radian, then since the radius is 1, then the distance from is actually 1. That means on this number line, we are really at 1 on the number line right here. This is 1. And 2 radians is about 115 degrees or so it's about right here. So that's number 2. And 3 radians is about this much. 3 radians is 3 times 57. So it's 170 something right here somewhere. So that's number 3 and so forth. Now, remember, now every angle here can be represented by a real number, right? That's a very, very important feature because we can work with real numbers instead of angles, okay? And what about negative angles? Well, if you go this way and you go negative 57 degrees, we can wrap this number around, and this would be negative 1 right here, and then negative 2 and so forth. So negative angles can be represented by real negative numbers, right? Very useful. So let's practice with this. So where is this real number? 3 pi over 4. Now remember, 3 pi over 4 in degrees, that's 3 times 45, so it's 135. So 135 is about right here. But what is this number? What is the length from actually here to here? Now to do that, we have to use a calculator and find out what that is. So let's say, so that would be 3 times pi and then divided by 4. That is 2.356. So this number is about 2.36, something like that, right? So it's a real number actually. So this is a number line right? So that's a real number, 2.36. So this angle turns into a real number, 2.36. What about the negative 2 pi? Well, negative 2 pi, we know that's a negative 360 degrees. So you start from here. If you start from here, you go around negative 3. And now this distance all the way around is going to be negative 2 pi, which is negative 6.28, right? We know because we know pi is 3.14 approximately. And what about negative 2? Well, negative 2 radians, we don't know how many degrees that is, but we know we can convert it to degrees, see what it is. Negative 2 times, how do we convert to degree? We divide by, multiply by 180 over pi, and that is negative 114 degrees. So that is negative 114 degrees here, up to this one. And this number right here, of course, on the number line, this would be negative 2. So that's 2 units. All right, what about 117? Well, that's 117 degrees. I mean, radian, not degrees. But how many degrees is that? Well, let's see, 117 times 180 divided by pi, that is 6,703 degrees. Now, how many turns do I have to go in order to make that angle? Well, I don't know. I divided by 360. See how many 360 degrees are in it? There are 18. So I'm going to multiply 18 by 360. See how many turns I have to take out of this. So I'm going to round it to 2 decimal places. 6703.61 minus 6480 is 223.61. So what I have to do is I have to go around here. How many times? 18 times. 1, 2, 3, 4, 5. I'm not going to do it. But here this is 18 times. Much more? 223 degrees, 0.61 degree. And I ended. Now what's that? What is that number on the number line? Well, you have to open this number line. So that would be a number, right? You can open it to the right. I don't have a space to open it to the right. So that would be that number right here, 117, right? And that's the idea. So any angle can be represented by a real number. All right, now we're going to talk about the 6 ratios that are foundation of trigonometry. And those 6 ratios historically, they have names. And they come from, there are 3 different ways to define them. So we're going to define them first using a right triangle. You probably heard about this in geometry in high school. So in a right triangle, there are 3 sides. 2 of them are called legs, right? And this one is called hypotenuse. Hypotenuse and 2 legs. Now, there are 6 different ratios you can write using these 3 numbers, A, B, C. And they're all given here. Either B over C, or A over C, or B over A, or reciprocals. You just flip them, right? Now, these have historically, they have names. And the names come from a long history of mispronunciation, mistranslation, misinterpretation, and all that. So it ended up with sine that has to do with sinuses like in your nose. Where does that come from? Well, you can read in Wikipedia and understand why we call it sine. It comes from Arabic language and Latin, and it's a combination of all that. So you can read about that. The names are historically given to us, so we're going to use them. So the sign of this, and we're going to define these ratios, 6 ratios, using in reference to an angle inside this right triangle. So this is the angle theta here. So we're going to define this ratio B over C to be the sine of this angle. And the sine of this angle is opposite over hypotenuse. Opposite over hypotenuse. Cosine of this angle is adjacent. Adjacent means right neighbor to it. But there are 2 of them that are adjacent. But this one has a name already. It's called hypotenuse. So when we say adjacent, we mean this one. So cosine is adjacent over hypotenuse, right? And tangent of this angle is opposite over adjacent. Now the rest of them are just reciprocals of these. So cosecant is 1 over sine. Secant is 1 over cosine. And cotangent is 1 over tangent. Now some students get these confused, but remember, to remember which one is which, cotangent, people don't get confused, is a reciprocal of tangent. They both have tan in them. But the cosecant is actually reciprocal of sine. So the way I memorized it when I was in high school was to think of one co. So if you say that cosine is actually, if you say cosecant is reciprocal of cosine, then we have 2 cos. Doesn't work. If you say sine is a reciprocal of secant, it doesn't work because we have no cos. So it has to be only one co. Cosecant 1 over sine. Secant 1 over cosine. All right, so there is a limitation, of course, a major limitation in this definition, and that is the angle is kind of stuck in a right triangle. And we can't make huge angles like, 10,000 degrees. How do we make 10,000 degrees here? Doesn't work, right? And we need large angles because in application problems, we need angles to be actually any real number. And here we are stuck in this right triangle. So let's liberate that angle with the second definition. So the second definition, what we do, here is the right triangle. We're going to take this angle, liberate it from triangle, so there is no more triangle. So all we have is an angle with the vertex, initial side, and the terminal side. We're going to take that vertex, put it at the origin in the coordinates plane, and initial side would be positive x-axis, always. We fix it here. That's the initial side. And the terminal side makes the angle. Now, here's the terminal side. We're going to randomly put a point somewhere on the terminal side. It could be anywhere. Here, 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 doesn't matter. Let's put it somewhere right here, right? So we're going to put it there. And we are going to call this distance r, right? That's the distance. And the angle now doesn't have to be just this angle. It could be any angle that ends up here. So it could be any positive or negative angle that ends up in this place. So the terminal side of the angle is here. We liberated the angle from the right triangle. We redefine the ratios this way, right? So we're going to define them this way. Now this angle is liberated. So I'm going to put the theta here instead of here. So this is not the angle we're talking about. We are talking about any angle that ends up here. So we're going to look at the x and the y coordinates of that point, which is basically x and y. And we are going to use x, y, and r to define our ratios. Sine of theta we're going to copy kind of from right triangle, but don't think of a right triangle. Right triangle is gone, right? So we're going to think of sine of the angle as y over r, cosine is x over r, secant and cosecant are reciprocals of those, tangent is y over x, and cotangent is x over y, right? So notice that the x here, right, we know that cosine of theta is x over r. Now if you cross multiply, then the x coordinate is given by r cosine theta. And we know that sine is y over r, and if you cross multiply, you get y equals to r sine theta. So that means the coordinates of the point on this circle, which is not a unit circle, are given by r cosine theta, r sine theta, right? Now, what does this do for us? Well, is first of all liberated the angle from a triangle. Now we can have positive and negative angle, right? But what it doesn't do is what we wanted, and that is we want an angle to be just a real number. If we can do that, then we have the best definition, okay? So here notice that r squared is x squared plus y squared, right? And that is true here. Okay, so now can we make this definition even better? And the answer is yes. So we're going to use the same setup, except in the third definition, we are going to put the point somewhere on the terminal side such that the distance r equals to 1. So we make a unit circle. And now we can easily see that if we use the same definition, sine would be y over 1, but 1 doesn't, so we're going to just say sine is y. Cosine is x over 1. Remember, r is 1, right? So it would be just x. And the rest of them are related to sine and cosine. Tangent is y over x, and the other three are reciprocals. All right? So now notice here that now x is actually the same as cosine of that angle, and y is actually sine of that angle. And we knew that already on a unit circle. The x coordinate is cosine of the angle, and the y coordinate is sine. And now, since the circle is unit circle, we can think of the angle as arc length. And now we have the advantage of angles are actually real numbers. Plus, we liberated theta, the angle, from the triangle. So now we can make any angle, positive or negative, we can think of them as numbers, real numbers, and we have all 6 ratios. Okay, that's the third definition. And we're going to work with these a whole lot more in this chapter. But for now, those are the 3 different definitions of 6 ratios. So I talked about that already. Notice that in a unit circle, this x coordinate is cosine, and this y coordinate is sine, right? Now, right away, we can think of first of all, let me talk about this notation, that when we write sine squared t, by that we mean what? We mean take the sine of t, the ratio, and then square it. Same is true for any ratio. If you see this notation, this means the ratio to the second power. Also, you notice here that this is a right triangle here. So sine squared plus cosine squared has to be 1. And that is a really important identity in in trigonometry. So sine squared plus cosine squared of an angle equals to 1. So this is called Pythagorean identity. And we can prove it using the three definitions that we had. Okay? So let's look at a point on the unit circle, right? And we want to find the ratios for that angle. Now, of course, there are infinite number of angles, but there are angles that are famous, and we need to know the sine and cosine of those angles. See? Those, especially those three, because 0 degree is easy. What's the cosine of 0 degree? Well, we know on the unit circle, this is 1, 0. So cosine of 0 degree is 1, and the sine is 0. Now, what's the sine and cosine of 90 degrees? Well, that's 0 and 1. So cosine is 0, and sine of 90 degrees is 1. Right? So those are easy. But the other angles, well, how do we know what the other angles are, right? So we have to calculate them. So let's do that. First of all, if we are given the x and a y coordinate, then we know this is cosine and this is sine. How do we know that? Is because this is a unit circle. Now, this is important to understand. If you're not on a unit circle, don't think that x and a y coordinate on a circle are actually x and a y are actually cosine and sine are always x and a y coordinates. That's not true. You have to be on what? On a unit circle. That means this has to be, the radius has to be 1. Otherwise, this you have to multiply the radius by it, right? Let's say you're over here. Then the x and a y coordinates is going to be r cosine t and r sine t, right? And that's what the difference is. All right, so this is easy. We're given the answer, right? Or what about here? Well, 270, we end up here. And obviously, the cosine of 270 is 0, and the sine is negative 1, because we are on unit circle. What about negative pi? Well, negative pi, we're going to put this point on the unit circle and realize that cosine is negative 1 and sine is 0. Right? All right. Now, here is the Pythagorean identity that we can prove easily using any of the definitions that we talked about. So if we use a right triangle, we know that sine here is b over c and cosine is a over c. So if we substitute those for sine and cosine and square them, we end up with b squared over c squared plus a squared over c squared, which is have the same denominator. So, and we know by Pythagorean identity from geometry that this is the same as c squared, and c squared over c squared is 1. So that's one way we can prove this. Second way is to use this definition, which is the second definition, right? Remember, the sine and cosine were given by y over r and x over r. If we substitute, we end up with x squared plus y squared over r squared, and here we see that x squared plus y squared equals to r squared, right? Again, from Pythagorean identity in geometry. And we know r squared over r squared is 1. So that is how we prove it. And the easiest proof, of course, is unit circle proof. We know that here x squared plus y squared equals to 1, and x is cosine and y is sine and x is cosine. When you square them and add them, we end up with 1 anyway, right? So you can prove the Pythagorean identity using any of the three definitions that we talked about. All right, now what about the angles? 30, 45, and 60. Now remember, for these ratios to be useful, we have to know what the ratios are. For example, think about it. If you put a stick on the ground like this, let's say you know what the length of the stick is, and then you know the length of the shadow of the stick in the sun, right? Then if you know this angle, how do we know that angle? Well, if we know the ratios of the angle, let's say if we know the ratios of, if you know this and we know this, we can also find the hypotenuse here, right? And then if I know, let's say, sine of alpha equals to, let's say, some number, right? Now, if I take this and divide it by this length, and I get that number, then I know that this angle has to be whatever angle that sine of it is, this number, right? So it's very useful to know the ratios. Now, why would we want to know this angle right here? Well, because that angle is the same as the angle that the sun rays make with the horizontal. So in different seasons, you might want to know what the angle of the sun is and how it is changing, so we can understand how, the sun and the earth and seasons actually are related and behave. So it's very useful idea. So we got to know the ratios in order for them to be useful. So the first ratio I want to talk about is 45 degrees. So we put a point here in the unit circle and we say, okay, if this angle is 45, then what are the x and the y coordinates? That means what is cosine 45? What is sine 45? Now, if you go back to a right triangle, we know in a right triangle, if this is 45, then this has to be 45. Why? Because in a right triangle, the angles add up to 180. Now, if this is 45 and this is 45, then this triangle is isosceles. That means these two sides have to be equal. If this is x, that has to be x too. Or you can consider both of them to be y, it doesn't matter. So if this is x, this is x. Or if this is m, this is m, doesn't matter, right? So this is x, this has to be x. Then x squared plus x squared has to be 1. See that? That means 2x squared has to be 1. That means x squared has to be 1/2. And x has to be plus and minus. But we don't care about the minus because we're looking for a positive number here. These numbers are positive, right? Both of them. So we're going to take the positive 1 over square root of 2, rationalize it, and we get square root of 2 over 2. So we know that the sine, the cosine, which is x, is actually a square root of 2 over 2. And we know since x and y are the same, then the sine has to be the same as well. So right away we found, right now you should be able to memorize all this. Cosine and sine of 45, they're both the same and they are square root of 2 over 2. All right, what about 30 degrees? Again, we're going to put a point here and assume this is 30 degrees, right? And now, if you think about this, if you make another point here, you see this triangle right there, this big one? Since we know this is 30, then this has to be 32, because this is symmetric here. So this is 60. And if this is 60, well, remember this is 90 and this is 90, right? So this has to be 60 and this has to be 60. So all three angles here are 60. So that means this triangle right here is equilateral. That means all the sides are the same. Now we know that the distance from here to here is 2 times y, because each of these is y units. And that makes these actually 2y as well, right? So that's 2y, this is 2y, and that's 2y, right? Okay, now, so what is the sine of 30 degrees? Well, would be this distance here, which is half of 2y, which is y, divided by hypotenuse, which is actually 2y again. So y over 2y, the y goes away, so we get 1/2. So the sine of 30 degrees is 1/2. What's the cosine? Well, we use the Pythagorean identity. Cosine squared equals to 1 minus sine squared, and you just substitute. And again, we need a positive number, so it would be a square root of 3 over 2. So now you know what? You know cosine of 30 degrees, square root of 3 over 2. And sine of 30 degrees, 1/2. All right, what about 60 degrees? Well, 60 degrees, again, we can put the point here, use the unit circle again. And remember, in this one, we didn't use unit circle. We assume this is just r. And in this here, for 60 degrees, we assume is a unit circle. And so if this is 60 here, right, then this is 30, right? So that's the 30 degrees. And if you drop a perpendicular here, and this is 90 as well, then this, oops. So this triangle right here, again, would be an equilateral triangle, right? So that means all the sides are the same. So why? Because if this is 60, right, then this is 90 here. This has to be 60 as well. So we got 60, 60, and 60. So that means this side right here is 1, this side right here is 1, and this side right here is 1, right? Now, since this is an equilateral triangle, right, again, let me go over this one more time. If this is this side right here is the radius, so it's equal to that side, obviously. If that's the case, then these two angles have to be the same, right? But we know this one is 60. If this is 60, then the other one has to be 60, right? So these two have to be, see, let me do this again. So this angle has to be equal to this angle, but we know this one is 60. How much is left for these two? 120. But since they have to be equal, each of them has to be 60. So this is an equilateral triangle. And in an equilateral triangle, from geometry, if you have an equilateral triangle and drop a perpendicular from one angle, from one vertex to the side across from it, that divides this into two equal parts. That's from geometry. And you can prove that these two triangles are actually the same. They have the same size. So that means these two are the same. This side and this side. Now we know the whole thing is 1, so half of it is 1/2, or 1/2. So now in this little triangle here, we know y squared plus 1/2 squared equals to 1 squared. And from here, we can find y. Again, we're looking for a positive number. So what is the sine of 60 degrees? Is the square root of 3 over 2. Right here, right? And the cosine of 60 degrees, of course, is the same as this x here, x over 1. And that's just 1/2. So cosine 60 is 1/2, and sine 60 is the square root of 3 over 2. So here is the summary of what we just did for cosine and sine. Now for 0 and 90, of course, we don't need to to memorize anything because it's obvious what the values are, right? So this is 0, 1. And so now for these, it's not obvious what the values are. You just have to memorize them, right? And those are the values. So as a student in trigonometry, if you don't have these numbers memorized, people are going to talk behind you and say things about you. You got to memorize those, you know. So if you don't, then if somebody asks you, you know, what is sine of 30 degrees and you have credit for this course, you tell them you have credit for trigonometry and you don't know what sine of 30 degrees is, right, which is right here. Then you say, I took trigonometry with Mr. Davidson. Okay, remember that name, Davidson. All right, so what about calculators? Can calculator find the values for us? Well, yes and no, both. Because if you don't know how to use it, no. Now, what happens if I put cosine of 30, let's say cosine of 60 in the calculator? What do I get? Well, I get 0.5. That means the calculator, how does the calculator know that that 60 that you put there is in radian or degrees? Well, you have to set that up. Under mode, you see right now, the mode is in degree. If I change it to radian and then put cosine of the same thing, I'm going to get a different answer. Why? Because calculator thinks that 60 is 60 radian. Now, what is 60 radian in degrees? Well, you have to multiply by 180 divided by pi. So that's 3,437.75 degrees. This is the cosine of that angle the calculator is finding for you, right? So it's important to know whether we are in degree or radian. Now, if you put cosine 5 pi over 3 and you're in radian mode, you get 0.5. But what if you're in degree mode? What do you get? I've got that. So let me put that. So cosine 5 pi over 3 is 0.5. Why? Because the calculator is in radian. Now, if I change the mode to degree, now what does the calculator give me? That is the same thing, right? I get the, see? Why? Because the calculator now thinks that 5 pi over 3 is actually 5 times pi divided by 3, which is 5.23 degrees. So that number is cosine of 5.23 degrees. That's what the calculator is finding. So it's important with the calculator to know whether you're doing radian or degrees. Okay, what is a reference angle? Well, remember, if we know, let's say we want to find the sine of 225 degrees, right? There you go. We want to know the sine of that, or cosine of it. So what are sine and cosine of 225 degrees? Well, think about it. 225 would be 180 plus 45. So this angle is 45, which is the same as this angle. If you reflect it over here. Now, what are the cosine and sine of 45? We already know that, right? Cosine of 45 is square root of 2 over 2, and sine is square root of 2 over 2. So we know that this value, right here is exactly the same as this value except for the sign. And this value right here is exactly the same as this value except for the sign, right? So that means, let me clean this mess. That means the cosine of this angle is the same as what? Cosine of this angle, except is negative. So we say cosine of 225 is negative cosine 45, and so that's negative square root of 2 over 2. And the sine of this angle, that distance, is basically that distance negative. So sine of 225 is negative sine 45, so it's negative square root of 2 over 2, right? So it looks like with this trick, if we know the values of the angles in the, let's say you know the values of 30, 45, and 60, then you can easily find the values of the ratios for those angles as well. And also for these angles, right? If you reflect them this way and reflect it this way, so you see how many angles now we know the sine and cosine of? Many, right? All of these angles that are related to these three, 30, 45, and 60, now we can find sine and cosine of. Now, this is very useful because remember, the people who invented trigonometry, they didn't have calculators. So what they had to do, they had to make a table of values, let's say starting from 0 and going by 1 degree, right? 2 degrees, 3 degrees, and actually measure these values, right? And then let's say these are sine, right? So let's say they knew that the sine of 1 degree, which I cannot draw here, so they knew the sine of 1 degree, then they could find the sine of cosine of 181 degrees, right? Or 359 degrees, right? So this way, using a table for angles from 0 to 90, they could find the ratios for all angles. And that's what they did. So this idea of reference angle, which is basically this angle right here, is very useful. Now, so the reference angle is the angle that the terminal side of this angle. Now, it doesn't have to be exactly this angle, right? It could be any angle that ends up there. So you can go around like 10,000 times and get here. As long as the terminal side is here, then the reference angle is this right here. Why? Because they have the same sine and the cosines are just opposites, right? So if your angle ends up in the first quadrant, this is the reference angle. If it ends up in the second quadrant, this is the reference angle. If it ends up in the third quadrant, then that's the reference angle. If it ends up in the fourth quadrant, then that's the reference angle. So you see, we can actually define it to be reference angle is the smaller angle that the terminal side of theta makes with the x-axis. See? Not this one, but the smaller one. 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 So it's really easy to understand how to find reference angle, right? And you know why we're interested in reference angle? Because now we can convert all big angles into angles from 0 to 90. So So let's do some example. What's the sine and cosine of 11 pi over 6? 11 pi over 6 is 11 times 30 degrees, which is 330 degrees, right? It's easier to see it in degrees. So 330 degrees is all the way around here, and obviously it makes that a 30 degrees because it's 360 minus what? Minus 11 pi over 6, which is 330. 360 minus 330 is 30 degrees. Or you can think of it as this right here is 2 pi, and subtract from it what? That much. So 2 pi minus 11 pi over 6. 2 pi with the denominator of 6 is 12 pi over 6. It's minus 11 pi over 6 is pi over 6. So you can find it that way. So that's the reference angle. Now, we know if we, again, reflect it into the first quadrant, the cosine of this angle is the same as the cosine of pi over 6, right? And the sine is just a negative. So cosine 11 pi over 6 is the same as cosine pi over 6, which is 11 square root of 3 over 2. And sine of 11 pi over 6 equals to negative sine pi over 6, which is negative 1/2, right? Because we know this is the square root of 3 over 2, and this is 1/2. So that would be a square root of 3, and this would over 2, and this would be negative 1/2, right? Okay, here's another one. Negative 5 pi over 4. Now pi over 4 is 45 degrees. 5 times 45 is 225. So that's negative 225. So if you go this way, that's 180. How much more? 45. So the reference angle is 45 degrees. And if you reflect it to the first, in the first quadrant, you see sine and cosine of this angle is basically related to sine and cosine of this one. The sines are the same exactly. The cosines are opposites. And we know this angle is 45 degrees. So that's the square root of 2 over 2, square root of 2 over 2. So that has to be, the y-coordinate has to be square root of 2 over 2. And the x has to be negative square root of 2 over 2. So that's how we find the sine and cosine of that angle, right? Again, nowadays we use technology to do all that, but you have to be able to do this by hand in order to understand mathematical concepts that we're going to talk about. You have to be able to do these by hand. You cannot just say, okay, I have a calculator, forget about this. You have to be able to do these by hand like I'm doing here. And you got to know, you got to have to memorize those 6 numbers for 3 angles, 30, 45, and 60. Besides the fact that people will talk, behind you if you don't know those, you're not going to be able to understand mathematical concepts that we want to talk about in this chapter. And the next 2 chapters. Okay, find the cosine and sine of the following. Again, you can see easily. 7 pi over 3 is 7 times 60 degrees, 420 degrees. So that's 360 plus how much? 60. So that has to be 60. And right away, since this ends up in the first quadrant, the sine and cosine are exactly the same as sine and cosine of 60 degrees. Okay? All right, so now as you see the power of what we just did, see if you know these 3 numbers, then you know the rest of them. You should be able to draw this unit circle with all those points. How many points are there? Well, there are these 4 points, which are really easy to figure out because it's a unit circle. And there's 4 times 3, 12 of them, right? 12 of these, and 12 plus 4, that's 16 different points. In order to get all of them, all you have to know is these three. Then you can what? You can use, reflection to find the rest of them. All right. So I'm going to end this video here and continue in the next video. I'm sorry these videos are long, but I don't believe in short videos. You can't really talk about anything in a few minutes. Unless you're teaching procedural knowledge, for which you don't need a teacher. So if you want to learn procedures, just follow steps. You don't need a teacher to learn procedural knowledge. So that's why short videos don't work. Videos have to be at least 30 minutes. All right, so take care of yourself and others. I see you in the next video.